Hello everyone. It's my pleasure to introduce our today's speaker, Amanda Rubio from University of Sao Paulo. Amanda did her undergrad at the University of Sao Paulo, working on physics and astronomy. And later she joined Professor Alex Carcioffi's group at same university for her master. She finished her master in 2019, and now she's PhD student at the same university. Currently, she's at ESO, collaborating with Dr. Dietrich Bade. And Amanda specifically work on B stars, either isolated system or binary systems. And today, her talk will be about the accretion and decretion process in B stars. Amanda, please.
Thank you, Maziar. That was great. Well, hi, everyone. My name is Amanda Rubio. I'm from the University of Sao Paulo, but at the moment I am at ESO. I'm working with Dietrich Bade on B pulsation, but I'm also working with my supervisor, Alex Carcioffi, and Professor John Bjorkman at the University of Toledo on SPH simulations of BE stars. So I'd like to thank Carol for inviting me, and I hope you guys enjoy this presentation. Okay, so I'm going to start with a brief introduction. As most of you probably know, since we've had a lot of talks on BE stars on this working group already, BE stars are B-type non-supergiant stars. They are very fast rotators. They are non-radial pulsators. And the most interesting thing about BE stars is that they undergo episodic mass ejection. And from this mass ejection, a Decretion disk is formed around the star from matter that is ejected from the star itself. And this can be shown observationally in emission lines, pretty much in the Balmer series and also in some helium lines, linear polarization and access in the infrared as well. So focusing more on the Decretion disk, the theory that best describes the disk of BE stars nowadays is the viscous Decretion disk theory, or the VDD. This disk is going to work basically the same as an accretion disk or protostellar disk, except it's going to work backwards, because what maintains the disk is matter that is ejected from the central object and not matter that's coming from outside into the central object. But once this matter is in orbit, the viscous torque between the layers of the material is what's going to cause this disk to grow. And this viscosity can be parameterized by the alpha parameter from Chakra and Sunyaev. And this model pretty much explains very well the emission lines, the infrared excess, and the polarization that we see in the data of BE stars. Okay, BE stars are not very well-behaved system, but if they were, assuming a BE disk that's not undergoing disk formation or disk dissipation, the VDD model can reach a steady state. So it has a steady state solution. So if we assume that the disk is thin and isothermal and that the pressure gradient is very small compared to the gravity, the density structure of the disk is going to follow this equation here. So it's going to depend on the mass injection rate, so the matter that's coming from the BE star into the disk, and on the viscosity parameter. But this is very ugly. We can simplify it if we just say that the sigma is something that follows a power law with R going to this exponent m. For the steady state solution, m is going to be equal to. And it also follows that the azimuthal velocity is going to be Keplerian, so it has a Keplerian velocity field. Radial velocities are going to be very, very low. And the scale height of the disk is going to follow, also follow power law with this parameter beta that's usually for the steady state around 1.5, sorry. So for a very well-behaved perfect BE star, this is what we would expect. But BE stars are not well-behaved, and they can be very much not behaved when they are in a binary system. So there has been previous works that have calculated smooth particle hydrodynamics simulations for BE stars. So this is a snapshot of Manoglo et al. 2016, which did just that. And we can see that this disk is not very I don't want to say stable, but it's not very well behaved. So we have three main effects that are very important for binary BE stars. So the secondary is going to excite the formation of density waves in the disk, these two arms that we can see pretty clearly here. The disk is going to be truncated, so we can see there's pretty much no disk in the regions higher than the orbit of the secondary. And since the disk cannot grow, it's going to have an accumulation of matter in the innermost part of the disk. It's going to lead to a less steep density fall off. And we can see all of that in actual observations of the E stars. So the density waves can translate to V-on-R variation in lines like H alpha. So this is a dynamic spectrum of H alpha line for a BE binary system. And this is phase folded. So we can see this nice little dance that follows the period of the secondary pretty clearly. If the disk is truncated, it also means that its emitting area is going to be smaller. So this is going to translate into less flux in the radio region here. And the accumulation effect, well, if we have accumulation of matter in the innermost part of the disk, it means that this disk is going to be denser. So the density slope is not going to be m equal 2, it's going to be m equal something less than 2. And the usual explanation for this is that, oh, this disk is dissipating if it has an m smaller than 2. But we have found this trend for stable BE stars, such as AlphaCo and Beta CMI, which are very much not building a disk or dissipating a disk, and they have m smaller than 2. So this can be an effect of binarity. It can also be an effect of something else, like a variable viscosity throughout the disk or non-isothermal effects, but binarity cannot be excluded. And why is this important? Why am I talking about binary BE stars? Why do we care? We don't really know how BE stars become BE stars. We don't know why they rotate so fast. And one of the ideas for how BE stars acquired their very fast rotations is that they were once in a post-mass, they were once in a system that was transferring mass, so a binary system with mass transfer. So we had two stars. One of these stars is going to receive mass, and angular momentum is going to start rotating very fast and become a BE star, and its companion is going to become either a compact object or a stripped star. And some recent works have shown that there's actually quite a lot going for it. So Clement et al. 2019, for instance, found the SED turn down, which indicates the truncation of the disk for every single star that they looked at, and that they had good enough radio data to really confirm that there was an SED turn down or not. Bodensteiner et al. Found no BE plus main sequence star systems, which makes sense if they are post-mass transfer systems. We would not expect it to be a main sequence star. And Hastings et al., for instance, found the binary evolution alone, they consider in their codes, could actually lead to a number that will match the BE stars, the number of BE stars that we find in open clusters. So BE stars and binarity, binarity can be the thing that makes BE stars. So for our work in particular, what do we want to do? If binarity really is essential for BE stars, then we have to detect these companions, we have to characterize these companions, we have to understand how these companions are going to affect the disk of BE stars. And BE stars have been, binary BE stars have been studied before, but we are bringing some new stuff to the table here. And that's why I'm giving a talk. So what we're going to do is that we're going to simulate BE binary systems using an SPH code. And you can say, Amanda, that has been done before, but wait, we're doing something a little different. And we're going to look at the entire system. So not just the effect of the secondary on the BE disk, but on the region around the secondary and on the broader region around the system as matter is escaping the system. Okay, so just a quick overview of what is smooth particle hydrodynamics. It's a mathematical technique that's going to describe a fluid using particles, just to make things a lot simpler for everyone involved. And BE disks are perfect for SPH because they're gaseous disks, they have no dust, they are pretty much controlled by viscosity and by the gravity field of the BE star and of the companion if there's a companion. So SPH is really perfect for BE disks. Our code, I'm not going to get into too much details here, but our code uses this type of kernel. It has a variable smoothing length and also uses variable time steps. It is a modified version of the code that was used by Okazaki 2002 and all these other works, and most recently Mark's work with the simulations as well. But why am I saying that this is a modified version? I'm saying it's a modified version because we modified it. So one of the main things that is different about our code is that we're using the particle splitting option. So this is going to allow us to have a better resolution in areas where the density is very low, because in SPH, the way that we were using it, every particle has the same mass. So if a region is not very dense, it just translates to this region has very few particles. And this is going to mean for the disk in particular that we have a bunch of particles very close to the B star and very few particles in the outermost part of the disk, which is an area of interest for us because that's where the secondary is. So when we're using particle splitting, we have a mother or parent particle. And when this particle reaches certain criteria, so it fills certain criteria that we have defined, it's going to split. It's going to split into 13 little baby particles that have the same characteristics as the mother particle, except it's 1/13 of that. And just to be clear on our criteria, the parent particle must have less than 70 neighbors. Its mass cannot be smaller than 4 to 10 to the -4 of the initial particle mass, which is the mass, the base mass that every particle has at the beginning of the simulation. And it has to be at least 10 times away from the B star. Why? Basically, we want to stop particles from splitting in areas where we already have a lot of particles. So the inner BE disk, close to the BE star, we have a lot of resolution there. We know exactly what's going on. We don't need more particles. We need more particles further away from the BE star in areas where we would have very few particles before. So that's our criteria for splitting. And another modification that we did was to change the size of the sink around the secondary. So our simulation has basically two types of particles. We have gas particles, which are the particles that compose the disk, and we have sink particles, which are the two stars. So those are the particles that control the gravity field. They have the gravity. They are the particles that are going to accrete gas particles that come too close to them. So they're going to behave as the two stars. So for previous simulations, such as this from Panolo et al. 2016, the size of the sink of the secondary was set to the radius of the Roche lobe of the secondary. So everything that came inside this region was accreted, so it leaves the simulation, and that's it. In our simulations now, we set the size of the sink to be the physical size of the star itself. And this is going to allow us to go from this type of simulation to this type of simulation. So let me just zoom in. This is what we could see before. And this is what we can see when we have particle splitting and when we have the small Roche lobe around the secondary. Of course, we had to test these modifications. We're not actually breaking the code and we were seeing things that were not real. So we ran 4 simulations that are the same, except that particle splitting could be on or off, and the size of the sink could be either the Roche lobe or 5% of the Roche lobe. So if we look at this upper plot here, the simulation in green is what we would have before. So we have no particle splitting and the sink particle is very, very big. And the pink one is what we have now with particle splitting and with the small sink radius. So we actually have a clear overdensity here in the dotted line, which is where the secondary is. So this is the thing that we have different in our simulations. We can see the stuff around the secondary and we can see the stuff that is beyond the secondary, which you could not see in the previous simulations at all. So for my work, I am exploring 3 different parameters. I'm keeping the stellar parameters the same. I'm keeping the mass ejection rate the same. The radius of the secondary is the same. The orbits The orbit of the system is circular and it's coplanar with the BE disk. So this is a very, very well-behaved set of BE binary systems, but I'm changing the viscosity of the disk. I'm changing the orbital period of the system, and I also changed the mass ratio. Okay, so before we really begin showing the results, there's two things that I need to clarify. So one thing that we are doing is that we are stacking time steps. Once our simulations reach a sort of steady state, that means there's going to be no difference between subsequent time steps, except that the system is going to rotate because it's in a steady state. The mass being injected and the mass leaving the system is pretty much always the same. So what we are doing is that we are freezing the rotation and we are stacking a bunch of different time steps together and just collapsing them as if they were a single time step. So this is going to increase our resolution a lot more. And something else that we are doing is that instead of looking at the azimuthally average quantities of the disk, because as you can see, this is one snapshot of one of our simulations. As you can see, like this, depending on which azimuthal direction you're looking at, you're seeing very different things. So we decided to divide our simulation as if it were a beautiful cake. So we have different cake slices that we're calling wedges. And we can look at the quantities such as density or velocity of the particles inside these predefined regions so that we can really characterize what we would see if we would look in these particular regions of interest. Okay, so as you can see, we have some very defined regions in our simulation. We have something that we are calling the inner BE disk. So things inside here are pretty much controlled by the viscous torque and by the gravity of the secondary. Then the primary, sorry. And here we have something that's being very much disturbed by the presence of the secondary. We have the two arm density structure, for instance. Then we see that one of these arms is actually connecting to the secondary, which is here, very tiny, you probably can see it. But we have this region that is not really the arm anymore, it's just something that is connecting to the secondary and dumping matter into the Roche lobe of the secondary. Then, of course, we have the region around the secondary itself, which is very interesting. We have never really looked at this region with this type of simulation before. And we have also everything else that is around this, which is the circumbinary structure. So we're going to look at each of these regions individually and characterize them. Yes, exactly. So first, let's look at the inner BE disk. What is the region that I'm calling the inner BE disk? So what I'm plotting here is the density of for two different simulations. So they both have 30-day period, and they have this one has an alpha of 0.1, so a very low viscosity, and this one has alpha of 1, so it's a very viscous disk. What we're calling the inner BE disk is the region where this isodensity contours here are still circular. So this is a very well-behaved region. Like the density is not yet perturbed by the secondary, as you can see it's going to be as we go further away from the primary. In this case, the secondary is like around here for both of the simulations. So the inner BE disk is this region here. And we can also look at that in a different way here. So again, this is the same simulation that I was showing before. So this simulation is this, and the other one is this one. So this one has a very low viscosity, this one has a high viscosity. And we are making good use of our wedges. So each of these lines represents each of these quantities that I'm plotting along one of these wedges. So the brown wedge here is the one that's looking towards the secondary, which is pretty clear when we see that it's the one that has the overdensity here when we look at the surface density of the system. But yeah, what we can see here is that the azimuthal velocity that I'm plotting here for the inner disk, so until about 10 stellar radii, a little less than that, this is textbook Keplerian. This is beautiful. And it's pretty much the same for the higher viscosity disk. This is a Keplerian disk. This is gorgeous. For the low alpha, for the high alpha, we also have a textbook VDD steady state. m equals 2, perfect. This changes when we're looking at alpha equal 0.1, where we actually have a very, very huge accumulation effect here. This line here is actually like, it goes with m equal 1 almost. So it's a very intense accumulation of matter that's going on inside of this. And the scale height is going also with a higher exponent than the expected for a regular normal VDD scale height. So this means that the disk is puffed up. And here is another view, but we are just looking at the wedges of most interest, which is the wedge along the secondary, this yellow one, the wedge that takes a little part of the bridge region, or the strongest density arm, and the wedge that's looking behind the VD disk. And for most of the simulations, if you guys focus here on the innermost part, so inside 10 stellar radii, from simulation to simulation, it really doesn't change much in any of these quantities. So this is radial velocity, this is azimuthal velocity, but it does change pretty much just for sigma. So we have disks that have a steeper density fall off. So that's the inner BE disk. This is the region that's going to be most oblivious to the presence of the companion because it is closer to the BE star. So it is dominated by the gravity field of the primary and by the strong viscous torques that we have in the base of the disk. It's characterized pretty much by circular orbits of the particles. It is azimuthally symmetric pretty much. The accumulation effect can be quite strong when we go for lower alphas and a little bit for larger mass ratios. The scale heights are a bit larger than expected, so the disks are a little bit puffed up. And this is a region that extends to a few stellar radii at most. So it's very, very close to the BE disk. If we were looking at this observationally, what would tell an inner BE disk apart from a disk of a normal VDD of an isolated BE star? We would expect stronger emission lines since we have a denser disk, especially the lines that are formed closer to the star, such as helium lines, and perhaps stronger V-band magnitude. Okay, let's go to the next region. So we were looking at the inner disk, but now we want to look at this, what we're calling the spiral-dominated disk. So before we were looking at the region where the isodensity contours were pretty much circular, but now we want to see the region where we have this messed up density isocontour. So we clearly have something that has this two-armed structure here and also here. This is really clear when we look at the radial velocity of the particles, because the density arms are pretty much created by this change in the velocities of the particles, because it's going to change their orbits, so they're going to accumulate in certain regions of the disk, and that's what gives the impression of these density waves. We can see that the amplitudes for the radial velocities are a little bit higher when we have a higher viscosity parameter, which makes sense, but they are not like much lower than that for lower viscosities. Now, if we look again at our view with many different wedges, if before we were looking at the inner disk region where everything was very azimuthally symmetric, now we're starting to see some very messed up things happening. So here in the radial velocity is pretty much what I was showing before, only we were looking at it in a 2D version and looking along straight lines. So the rotation and the spiralicity of the arms is being translated into this up and down curves that we see here in the radial velocity. We see a little bit of a staircase-like structure here in sigma. So we have a little tuk, 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 as the density waves are traveling along these different wedges. And our azimuthal velocities are also being a little bit messed up. So this is deviating from the VDD. This is where the companion is really making itself known and saying, hello, I am here, and you are no longer a steady state VDD solution. You can no longer behave like that. And it's also interesting to look at the scale height of the disk, because it was very, very nice textbook VDD before, and it begins to be messed up by the presence of the companion as well. And of course, this is one of the things that creates the density arms. The eccentricity of the orbits of the particles around the primary star begin to ramp up as well. So this is the spiral-dominated disk. So the companion is really messing up the disk, and because it's affecting it sidely. This region is going to be characterized by elliptic orbits of the particles. The two-arm density waves are traveling through the disk. It's going to, everything pretty much is going to deviate from the VDD solution at this point, from this point onwards. And the disk, as we can see, is smaller than the disk of an isolated BE star. And as we discussed before, this can be seen in the VNR variations of age-alpha lines, and also can be seen in the SED turn down when we cut the region of most density because of the presence of the secondary. We don't want to call it truncated because, as you saw, there's a lot of matter that actually exists beyond that point. So it is a really big drop in the density. Is this going to work? No, the video is not going to work, but the video is going to show pretty much what I'm showing on this plot here on the side. So these are synthetic age-alpha lines calculated from SPH simulations. This is courtesy of Mark Suffolk. Thank you, Mark. And what we are seeing here is different phases of this BE binary system. And as you can see, as the disk rotates, the age-alpha profile is going to be really, really, really messed up depending on which part of the disk is facing towards us and which part is not. So this is one very clear effect of what we expect to see that is caused by the influence of the secondary acting on the BE disk. Okay, let's go to the next region. We have here, as you can see, one spiral density arm, and we have another spiral density arm, and this one is connecting to the secondary. So let's look at this little region here that's actually the bridge between the secondary and the BE disk, which I used all of my creativity and named the bridge. So here I'm plotting the Lagrangian equipotentials and what we're calling the binding energy of the particles. So this is the energy of the particles when we consider the gravitational forces involved. But this is not like an 100% considering every force involved in the system. This is mostly to give us an idea if these particles are bound to the system or not. And as we can see, the mass transfer from the BE disk to the secondary is not really a Roche-Loeb overflow, because the disk has rotation. So the particles that are here close to the L.1, they have a rotational component. So this is going to form a structure that is leading the secondary. The secondary is moving in this direction. So so this region here, which is bound to the system, is what we're calling the bridge. And it's dumping matter from the BE disk right inside the Roche-Loeb of the secondary. And as we can see, this is a little spoiler, some of the matter is leaving the system to the point close-ish to the L2 point. So now we can look at our wedges again, but we can concentrate our wedges in the region of interest, which is from this radio onwards, and selecting only the part of the disk of the secondary here. So what's interesting to see is that by far this is the region that has the most matter when we're looking at this particular radius. So since we're looking at straight wedges and the structure is actually like a spiral shaped, we see this staircase little structure, which is following the density of the arm. We can see that the radial velocity is increasing inside the bridge. So this matter is being dumped with force into the Roche-Loeb of the secondary. These particles are really being accelerated towards it. And that's pretty much what characterizes the bridge. It's not a very that much of an interesting region, unfortunately. So this is just the region that's going to connect the B disk to the secondary. It is a part of the spiral-dominated structure in a sense that it continues with the same type of behavior. Only now it's connecting to something else. So it is the leading structure. It's leading the secondary. It's by far the highest density. Has the highest density for this radial region that we're looking at. It has increasing radial velocity, so it is accelerating towards the companion and is gravitationally bound to the system. Since this region has a very non-negligible density, we would expect maybe to see it also in VNR variations in N-alpha, giving a stronger asymmetry when we look at one of the arms or the other, since the bridge is pretty much part of the stronger arm. Okay, and now we can look at the region that was a mystery for the other BE star simulations, which is the region around the secondary. So for that, we're going to change our perspective a little bit. When I showed this type of images before, we were centered on the primary, but now we are centered on the secondary. So we are looking at the azimuthal velocities and the radial velocities in the frame of reference of the secondary. So if we have the structure that is rotating here, it's actually rotating around the secondary. So this is, so the particles have a rotational component that is really quite high. It's around 200 kilometers per second. But we also have a non-negligible radial velocity component. So this is the matter that's coming from the bridge, and it's coming towards the secondary with a lot of velocity, and it's flying past the secondary with still a lot of velocity. So we don't really, this is very much not a Keplerian disk. This is a rotating structure from what we can tell, but a lot of the particles are really just flying past the secondary rather than forming this very well-behaved disk structure around it. So this is very much not VDD, not a baby VDD disk around this secondary. That's actually accretion. And it's very interesting that when we look at high viscosity, we still have a rotational component, but it's much, much lower than what we had for the lower viscosity. And we still have, again, a very much non-negligible radial velocity going on as well. So for this case, it's very much not a disk. We can say this for sure, but it is something that rotates. It has a bit of a rotation around the secondary, but it's probably just matter being flung out by the secondary to the back of it, which is where the L2 point is. So we can look at our wedges again, but this time we are centered on the secondary. So the orange wedge here is looking back at the BE star, the green wedge is looking at the arm, and the blue wedge is looking the backwards of the back of the secondary, which is where we have the L2 point. So interesting things to see. We have a much, as I said before, we have a much stronger component of rotation for the low alpha simulation than we have for the high alpha simulation. But this guideline here is showing what we would expect if this disk was Keplerian, and we can see that it's not quite there. We have very strong radial velocities for both simulations, even for low alpha or high alpha. And we have this huge scale heights. So this is really not a well-behaved accretion disk. It's not really, it is a disk-like structure maybe for the low alpha, but we cannot call this a disk, and it's really, really not a well-behaved VDD-like system. So the circumsecondary region is characterized by this density that's going to depend very strongly on the viscosity and the period of the system. So how much matter we actually have inside the Roche flow of the secondary. The radial velocities have very similar amplitudes for the different simulations, but the azimuthal velocities are much, much larger when we look at lower viscosities. We see that part of the matter has to be accreted by the secondary, but part of it is also escaping the system through the L2 point that's right behind the secondary. And we can see that it is not at all similar to a VDD disk, even if it is like a backwards VDD disk, which would be accretion. Not similar at all. Well, if it was more disk-like, then we could expect to see double peaked emission lines, because we have seen this before in observational data of binary BE stars. So this is from Shavnovsky 2018 for the BE system HD 55606, which is a binary BE system. And these lines are not coming from the disk of the BE star. They're coming from the accretion disk around the secondary, which is very, very nice, but it's not something that we can reproduce with our simulations, at least not so far. Maybe our viscosity, if it was much lower than 0.1, we could reach something that was more and more disk-like, and maybe finally reach something that was that has a structure similar enough to an accretion disk to give us a helium line that looks like that. And finally, we're going to look at everything that is not inside of this, this red circle, everything that is outside of it, which I, again, used a lot of creativity and called it the circumbinary region. So it's everything that is beyond this point. And this is something that we had not seen before in the simulations of the E stars. We had expected that one of the arms would the BE star is losing this mass in the direction of the stew density arms, because that's where most of the matter is anyway. But it's very interesting to see that the strongest arm is going to focus matter into the bridge that's going into the secondary, and then part of it is accreted, but the part that is not is flung out of the system from behind the secondary, and this is the region where we have the highest density. So most of the matter that is being lost by the BE star is being lost through this arm here. And what's not being lost through this arm and that has not been accreted by the secondary, the BE star is losing from the other arm that's going to wound around it and then connect to this arm, forming one gigantic one-armed structure around the system. And when we look at our wedges, we can see something like that. So if we look at the brown wedge here, which is the wedge of the secondary, we see that we have, of course, here's what the secondary is, and then we have this drop in density. But then we see that there's an increase in density for the purple wedge. And where's the purple wedge? It's right here. It's where we have this drop-like structure that's leaving the secondary and running in this direction. So this is the arm of the circumbinary structure. And where's the next denser region? It's in the red wedge, which is the next region where the arm is passing through. And then the next one is the green wedge, which is the next region. So it has a very similar structure to the density arms that I showed before. So it has the staircase-like structure, only it's very, very extended. And we see the same thing in the radial velocity. So we see increasing radial velocity here, increasing radial velocity in the purple wedge, which is the next one, increasing radial velocity in the red wedge, which is the next one. And even here for the azimuthal velocity, we still have the same structure. So there's not much that we can say about the circumbinary region, except that it's a flow of matter that is being flung out of the system after it has been focused by the arm, and then by the bridge, and then by the companion. So it is a tightly wound one-armed structure, because we have one arm that's going to connect with the other one later on. Matter that is going to escape from behind the BE disk, it's going to form this other arm, and then the two meet up and form one arm structure. And this is probably gravitationally unbound from the system. So these are particles that the BE star is losing into the interstellar medium, and it's never going to see them again. And maybe this can translate into radio emission, because some recent works have found some radio emission in BE systems that have shown SED turn down. So this system shows clear SED turn down, but if we look at the residue here, we see that there's a small increase afterwards. And as we saw in our simulations, we have, of course, the big density fall off where we meet the secondary, but we also have this increase in density when we go through the circumbinary structure. And this structure might as well, it can be also emitting in radio. So that little increase in radio emission can just be coming from the circumbinary region. So my conclusions, finally, using particle splitting has been really great because it's allowing us to look at regions of the BE binary system that we have not really seen in depth before in other works. The viscosity shapes the evolution of the matter in the system as a whole, so it's a very, very important parameter. It really changes much of the quantities on the simulations. We can finally study in more detail the secondary structure, so what's going on around the secondary, and we can compute the accretion rate onto the secondary as well. And for low viscosity, we see that the secondary has a very strong rotational component, and perhaps we can form a real, honest to God, accretion disk around that secondary if we went for lower and lower viscosities. So this was my presentation. Thank you very much.
Thank you, Amanda. Thanks for such a nice job and nice presentation.
Thank you.
Any question? So I have actually a question, Amanda. In your slide number 29.
29.
29.
Wait, 20 or 20 or 30?
29.
20.
Yeah.
This one?
Yes. So you say that for lower alpha, there is accumulation of mass, which is not in greater alpha. So I'm wondering, the growth of the disk is under control of viscosity, and the larger alpha should be like faster growth in the disk. I'm wondering,
Yes.
how do you explain that with lower alpha, we have more accumulation of mass in larger radii?
But that's exactly it. So the disk grows so much faster when we have a larger alpha,
Okay.
that it has a stronger radial component, and the disk that has a lower alpha is going to have less viscous torque, pretty much. So the torque that the companion is going to exert on it is going to be much stronger, and that's why the disk can't grow. So for the larger alpha, it has a very strong viscous component, so it's going to grow. The secondary is not strong enough to affect it yet, so the disk is allowed to grow further out. And then for the lower alpha, the effect of the secondary on the viscous torque, like the fight between the torque of the secondary and the viscous torque of the disk, is going to create the accumulation effect. It's going to make it stronger. That's what's going on here.
Okay, thank you. So we have a question from Michel Coeur. He has actually two questions. So can you read it from the chat, or you want
from the chat? Wait, let me open the chat. Okay, so Michel
can ask his questions, whatever you wish.
Hello. Oh, the first question is if the star is oblate or spherical in the SPH calculations.
The sync particle is spherical.
Very good.
Yeah.
And the second is more important question for me. How important are the effects of the radiation force in all these calculations? Because it's neglected here.
Yeah, it's pretty much neglected. So it would really change. I expect it would change a lot of things around the secondary, because like if we have some BE system, we have a lot of BE systems with neutron stars and things like that. So it's probably very intense stuff going on in that region. And if we have magnetic fields and things like that, that's something that we're not accounting for in our SPH simulations now. That's why I said it's the most well-behaved binary systems that you could find.
Thank you, Ananda.
Thank you.
Okay, so no more question?
No, there's two people with their hands up. Doug Guys,
Oh, okay.
I think, was the first one to raise it. So Doug, go ahead.
Hi, Amanda. Thank you very much for your very beautiful talk, and congratulations on these very nice simulations. I think they are really going to stimulate everybody's interest in trying to decide how we could explore these observationally. And one thing I would point out is that I think there's a great future for interferometry, to actually try
Yes.
to do angular resolution of some of these structures around at least some of the nearby stars. And in fact, I have a student at Georgia State, Peter Wysocki, who is using the CHAR array right now to explore some asymmetries in the disk of some of the classical northern BE stars to try to see if the V over R variations that we see in H alpha actually correspond to maybe some spatial structures around the stars, presumably from the bigger structures, which are, I guess, the big spiral structures that you're seeing in your simulations.
Yeah, and hopefully something from the bridge as well, right?
Yes.
If it's dense enough, yeah, fantastic.
That was my question. I wanted to go back to your slide number 40, if that's possible. I was really interested in this bridge region.
40. Here?
Yes. This is really interesting to me because I'm sure there are a number of BE stars that we have studied that are similar to what you're showing here, of having such interaction between the gas flowing across the L1 gap between the two stars. And you made the point here that you thought most of the flow was originating across the gap, going from the BE star to the companion ahead of the L1 point, exactly, just where you put your cursor on the extension. And I wanted to bring to your attention in the classical three-body problem, which is sort of at least similar to what you're dealing with here, there are what are called horseshoe orbits. And these are very unusual things. I think they were first discovered maybe in the Earth-Moon system. But these horseshoe orbits show that you can have material that crosses between the two objects and actually goes in both directions. And the sense of it is that if you think about the BE star disk, it's rotating Keplerian in the sense that you're showing here is a counterclockwise direction. And so material that's approaching from below the L1 point, as shown in your diagram, is actually got a higher Keplerian rotational velocity than does the companion. So that material is moving along faster than the outer material. It feels the gravitational pull of the companion and actually moves outwards. So in these horseshoe orbits, the material actually moves outwards below the L1 point. It gets involved. It actually, when it feels the pull of the L2, it changes and eventually gets into an orbit that becomes circumbinary, much like you've shown here. And on the other hand, the material that's in front of it, the gas in the BE disk is moving faster than the companion. And so in the horseshoe orbits, it actually goes the other way, that the material would cross in front of the companion, go across ahead of the L1 point, and then join into the BE star disk. So you'd actually have matter going in both directions.
Okay, I see.
Now, you didn't find this, but it might be because you're looking at the wedges. And to see something like I've been describing might take a higher spatial resolution, that you'd really have to go in and look at various places in your simulation. But why I brought this up and why this is interesting to me as an observer is there's a famous northern BE binary called HR2142 that's been studied a lot by Jerry Peters and collaborators. And in a paper that we wrote with her in 2016, Peters et al., 2016, we explored particularly this crossover bridge region in spectroscopically in this area for HR2142. And this star is close to edge on, is close to 90 degrees inclination. And we see what Jerry Peters described as orbital shell phases, orbital phase shell phases that as you observe this system and just before you see the companion moving in front of the BE star, just before that, which would be a view line looking just above the L1 point, you actually see positive radial velocities appearing in the shell line, as if material is moving across from L2 back over to the BE star. And then just after the companion crosses in front, you actually see negative shell line velocities, as if material from the BE disk is moving outwards towards the companion. And so in that paper, we made the argument that that there is in fact crossing going on in both directions, at least in that system. Now, maybe that's a very special system for several reasons. The disk is probably very, very full. But anyway, I just wanted you to be aware of the fact that at higher spatial resolution, the flows may be more interesting and more complicated. And I'll send you a link to the paper after the.
Please do. That's very interesting. Yeah, I really hope that I can do like a super wedge view where I can split this thing into 1,000 different wedges, and then maybe we can actually see something like that. That would be amazing. Thanks a lot.
Okay, Carol, I don't, because I'm not.
Yes. Oh, sorry. And then I'm sorry. I didn't realize you couldn't see who had their hand up. So yes. I'm gonna mispronounce your name, but Alik, is that correct? Anyway, please correct me if I've got your name wrong. And then Atsuo's got his hand up, and Amanda, Sally would like that your email screen up if you have time to do that at the same time you're listening to a question. Thank you.
Let's do that. Thank you, Carol.
Thank you very much for your talk, Amanda. Yeah, I had a question concerning more the circumbinary disk that you mentioned. So you say on one hand that it's probably material which is unbound, and that's what we could see on the color plot of the energy of the different material. And my underlying question is, what's your assumptions in terms of thermodynamics in the SPH codes? Can the material lose energy and become bound again after it went beyond the outer Lagrangian points? Or is it really like a disk-like structure if you plot the azimuthal speed, or is it mostly like a spiral which is slowly going outwards?
Yeah, so it's mostly a spiral going outwards. And the thing is, in our simulations, we set everything to be isothermal. So the particles don't really have a lot of room to transform energy into other types of energy. So yeah, that energy consideration that I'm doing is very basic. It's like, okay, this is a bunch of little balls that are rotating along with this very big balls in this co-rotating frame. So yeah, so we're not 100% sure if the material is actually unbound, but it has, from what we can tell, enough energy to leave the system for real. If that answers your question.
Yeah, thank you very much. Thanks.
Thank you.
Thanks. Atsuo, do you want to go ahead?
Oh, yes, thanks. Yeah, your talk was very, very interesting. Yeah, I'm very impressed. And I haven't thought about the existence of the circumbinary disk. So this is very interesting. So I have one question and one comment. One comment on Doug's comment. Yeah, Doug talked about three-body problem, and he talked about horseshoe orbits. But I don't know about horseshoe orbits, but this sort of leading tidal tail toward the tidal bridge toward the companion is due to viscosity. Okay, so B disk. So this shape of B disk is sort of tidal bridge. So if there is no viscosity, gas particles respond to the tidal potential instantaneously. In such a case, the B disk would be elongated toward the companion, but inside the disk there is viscosity, so the response delays, and so the gas particles in the B disk is rotating faster. So after passing, say, the point to closest to the companion, the disk starts deforming. So tidal bridge always looks like this. So sort of leading, but actually the response is delaying. That causes this kind of shape. That's my comment. And my question is that, yeah, is the particle splitting essential to see this kind of structure, circumbinary disk?
Yes, at least in the simulations that we run. So if I go back to the tests that we did, so if I go back to the tests that we did, where we have one simulation that has the same parameters but no particle splitting, so it would be the pink one and the bluish one here. We do see something, but we do not see as clearly as we do with the particle splitting. So if I were to limit what I'm plotting here for those blue simulations, what I actually have, like maybe more than 50 particles in this region or not, then this might disappear completely or something like that. So this huge gap here, for instance, and then this increase, I don't believe this is particularly real.
Okay,
So yeah,
thanks.
I would think particle splitting is kind of essential for that.
Thanks, Amanda. Alex has got his hand up. Go ahead, Alex, if Atsuo's finished.
I'm going to borrow Amanda's computer here. Just a quick comment on this interesting comment by the guys and then the comment by Atsuo, right? We are used to think on Roche lobe overflow, like there's a star. This star can be static, it's not rotating, and it expands. And then a material flows through L1 into the secondary, right? In this case, matter, like of the photosphere, of the atmosphere of the star, doesn't have any angular momentum. And that's a huge difference, right? In the case of these star disks, the outer part is rich of angular momentum because it has gained angular momentum through the disk evolution. And that's why it's a leading structure. It's a more or less the same analogy of the tidal bulge between Earth and the moon, right? The tidal bulge is always a leading structure because the moon, the Earth is rotating much faster than the moon is orbiting, right? So it's just an analogy that I find useful to understand the fact that the bridge is always going to be a leading structure in the star disks.
Thanks, Alex. We're just about out of time. Alik, did you have another question or is your hand just raised?
Yeah, that was a follow-up on the previous comments by Alex. So did you try to explore like counter-rotating configurations? Because I guess then it will make a huge difference for the size of the accretion disk around the secondary, because you can compute the circularization radius and it's going to be radically different whether the secondary is orbiting in the same direction as the decretion disk or the opposite direction.
Yes, that's something that would be very interesting to explore, but we do not have any simulations like that so far. But that's on the list, definitely.
Okay,
Thank you.
Great, thank you.
Well, I think we're just about out of time. Amanda, that was an absolute fantastic talk. Thank you. It was very interesting. And thank you. This was a great way to start off our year of seminars. So thank you very much, Amanda.
Thanks everyone for watching and for the questions. And I did put my email on the chat. So if anyone has another question or comment, please send it to me.
Perfect. So I hope to see everybody in another month. For everybody in our working group, you're going to get a vote for the BE Star executive on the 24th in about a week. So watch for that from my assistant in the dean's office, Stephanie Attardi, who will run the vote confidentially for us. So thanks for everybody for joining, and thank you, Amanda, for providing such a very interesting and a terrific talk.
Thanks again for inviting me. Thank you.